Hi, welcome to our classes. So in the last class, we discussed about the general structure of the metal-carbene complexes, the category of the different metal-carbene complexes like Fischer, Strock or alkylidene, vinylidene complexes, okay, mixed Fischer Strock type carbene complexes. And then we have discussed quite elaborately about the different type of metathesis reactions where the metal-carbene complexes act as efficient catalysts, and we have realized that the application is versatile, and you will see that it acts as a single key for multiple locks. That means a single catalyst can do various type of alkene metathesis reactions. Today we will discuss about the general synthetic protocols for the metal-carbene complexes, mainly Fischer Strock carbene complexes, and then we will study the reactivities following classes, and then we will come to the special reactions, which is actually the polymerization reactions to get the different hydrocarbon polymers where metal-carbene acts as catalysts. So let's discuss first the metal-carbene complexes, the general synthetic protocols. Why it is important? Because you know that before doing the any applications, we have to synthesize. We should know what are the synthetic protocols. If I need to design a new catalyst, how we will synthesize, how we will choose the precursors of the different carbene, what will be the reaction conditions. So those fundamental aspects we have to realize first. So it will give a kind of a guideline to make or to follow the strategy of different metal-carbene synthesis. So in this class, today's class, we will cover the concept of general synthetic protocol for both the Fischer and the Strock carbene complexes. Okay. So the key points will be Fischer, Strock synthesis, general strategic synthesis. So we know that generally the two type of carbene complexes, one is the Fischer and one is the Strock carbene, and we have realized that it is the general structure is like that. So it's formally there is a two bonds between metal and carbon, and you know that Cr2, it's a free carbene. This is highly reactive. Okay, we have already discussed very elaborately, and you saw that this free carbene Cr2 can exist as singlet and triplet, and this carbene complex, these free carbenes are highly reactive, and it gets stabilized by forming the complex with metal fragments, definitely with suitable metal species, precursors, and form this kind of metal-carbene complexes. Fine. And we know that now difference between the Fischer and Strock carbenes. So Fischer carbenes, you see that they generally form the low oxidation state. As example, like medial transition metals, okay, with low oxidation state, and medial or late transition metals. And the Strock carbenes are generally early transition metals with high oxidation state, and the formally two covalent bonds in Strock carbenes and Fischer carbenes. It's basically one is the covalent bond and one is the through pi back donation, and you see the metal-carbon bond for Strock carbene is quite stable, quite strong, and whether the Fischer is not that much stable, that much strong, and accordingly the polarity of the metal-carbon in Fischer and Strock is exactly opposite. Okay, like for Fischer, we know now that it in the Fischer carbene complexes, the C plus is actually the delta delta plus, and in the Fischer carbene, in the stock carbene, it is delta minus. Okay. So the reactivity on the carbon of the carbene is metal carbene is very much different, actually the reverse in the Fischer and stock. Now how to synthesize it? Okay. So this is generally synthesized by a metal carbonyl complexes. Okay, actually this is the first synthetic protocol followed by the E.O. Fischer. Okay, and I will give the specific example of the first Fischer carbene complexes synthesized by E.O. Fischer in 1964. So you see that here the Fischer carbene complexes, the general structure is like this one. Okay, O R, and this R, we know that we already discussed that this is the lone pair like oxygen, nitrogen. So it has a lone pair, that is a heteroatom, and it has a filled p orbitals, and this is the pz orbitals, vacuum pz orbitals, and it has a d orbital. So perfect matching, and that's why it can, this pz orbitals, it can accept electrons from here to here, and it is basically behave as a delocalized between MCO. Okay, so fully delocalized system and make it thermodynamically stable system. Okay, so if you, that's why if you consider the Fischer complex like let's say Z R, like that one. Okay, so it can, so I should not put the equilibrium sign, actually I should put the this is, I want to see the two different canonical structure. Okay, so one is possible is this one, A minus C Z, and this is R, so this is the plus. Okay, and another one is, so this has a lone pair. Okay, and so what is a heteroatom like oxygen and nitrogen, so this will be Z plus. Okay, and this will be minus. Okay, now so you see here this is, so it's basically formed like this one and that one. Okay, the contribution of this one is the major. Okay, however the contribution of the two canonical forms, this one and this one, depends on pi donation of what? Any idea? The pi donation of M d orbitals, M, Z, and obviously the R. Okay, so depends on the nature of the metal, Z, and the heteroatom, and the also the R. Okay, so however the major contribution is this one, where you will see that Z form delta plus and M is delta minus. Okay, and generally the Fischer carbene complexes are more common with chromium, molybdenum, tungsten. However, it is not limited, it is ruthenium, iron, okay, others, but these are the first synthetic protocols. So how we will go in more detail about the synthesis. So here you will see that this is the actually the first Fischer carbene complexes synthesized by E.O. Fischer back in 1964, and see the strategy. So you need a metal carbonyl here, like a tungsten carbonyl, okay, and then you need a alkyl lithium, so M minus Li plus, okay. So addition strong nucleophile alkyl lithium or even Grignard reagent or any alkali metal amide, and it attack on the carbonyl carbon and form the lithium salt, okay, of the anionic acyl or carbamyl ligand, okay. And the second step, that is the first step, and the second step is that the methylation of the lithium salt by the alkyl electrophile, okay. So here you see this OMe3 plus is a very good alkylic agent. In many cases in a laboratory we use this reagent to alkylate. However, it is not limited. You can also use the other alkylating agent, methylating agent, as example methyl iodide or methyl triflate, okay, you can use, no problem. And then what you will see, you will get the methylated Fischer-Carbene complex. So it will convert to the anionic to the neutral complex, neutral metal-carbene complex, and this is the synthesis of the Fischer-Carbene complex. This is the first report of the Fischer-Carbene complexes. So it's basically the CO5W, okay, OMe and Me, this one, fine. So this is this as written in other form actually. So this is basically the O plus, O plus, O minus. So as we discussed in the as we discussed here, okay, same thing, fine. So you see that generally two steps. One step is involving the a strong nucleophile, generally alkyl lithium, and then using a alkylating agent to alkylate the lithium salt. So here one thing to note, that in the Fischer-Carbene complexes is good to know, although it is not the synthesis slide, but it is good information and good to understand that this one, okay. So we, as I already told, that this is the major contribution, the of the canonical form, between the three possible canonical forms, due to the pi donation of the oxygen pi electrons. So here you will see carefully that two type of geometrical isomers are possible, okay. This is one, and any idea which one is the other one? Okay, you can guess it, okay. You see the double bond character between where it is between the carbon and oxygen, okay. So then you will realize that which one will be the other geometrical isomers. So here you will see that like this one. So now it is very clear that here cis-trans type of isomers, okay, are possible around the carbon oxygen double bond, okay. And due to the double bond character, here you will see this is double bond character, okay. However, this one is the single bond character, okay. The single crystal X-ray crystallography nicely proves about this single and double bond character looking at the corresponding bond lengths. So here, that's why you will see that restricted rotation, okay, restricted rotation around CO, okay, because as it is a double bond character, so it cannot rotate freely, okay. Okay, and you can very nicely monitor by the proton NMR spectra. However, there is a rapid interconversion between the two forms at room temperature. Okay, but if you cool down, let's say you record the NMR at minus 40 degrees centigrade, you may get two type of signals of these methyl groups. Okay, one will be this side near the metal, okay, and another one is the away from the metal center. So you will get a two type of signals for the methyl groups if you lower down the temperature. So here you will see that this also proves that the contribution of this canonical structure, okay, if you compare this one, okay, this one and this one, that this one is actually the major, okay, contributor. Okay, it's good to know while designing any metal-carbene complexes. Fine. Okay. So now we understood that how we make a simple Fischer-carbene complexes from starting from a metal-carbonyl complex. Okay. Now, as we already discussed that, and we already know that the metal-carbene complexes, okay, like this one, let's say ZR, okay. So this is delta plus and this is delta minus for the Fischer type of metal-carbene complexes. Okay. So this is basically a electron deficient olefinic bond. Okay. So obviously it is not carbon-carbon olefin, but it's a olefinic type of bond where one carbon is replaced by one metal fragment. So that's why this carbon is electron deficient. The carbon of the carbene, okay, is electron deficient in nature. That means it reacts with nucleophile. So nucleophilic attack is more facile. I think it is very clear now, okay, for the Fischer-carbene complexes. So it is now very clear that what I am telling you. So now you see that what may be the what strategy we can follow to make other type of Fischer-carbene complexes where the heteroatom is not the oxygen. Like here you will see, following this concept, okay, here you will see what it has been done. You take this Fischer-carbene complexes as a starting material, and then you react with amine, okay, and amine has a lone pair, so it basically acts as a nucleophile. It's very common, no, that amines can act as a nucleophile, and so it reacts with this amine reacts with nucleophile, and so it's basically reacts with here, and then it's become delta plus and it becomes minus. So this is the, see, this is the species, and then the elimination of methanol, okay, and you form the new Fischer-carbene where the heteroatom is amine, okay. So here you will see that this is a very nice synthetic strategy with the help of the carbon electron deficient nature of the carbon of metal-carbene, okay. And not only that, okay, we can also use this kind of precursor where here it's basically, you know that this is also fantastic ligand, and this is called the phenyl isocyanide, and the category of this kind of ligand is isocyanide. It is routinely used to make the precursors of different metal complexes, and this one is a labile, and also the it is more feasible. These ligands isocyanide is labile, very weak bond, and more feasible for nucleophilic attack, okay. Then carbonyl, then in carbonyl. So very easily the nucleophile can attack on the carbon here, okay, and you can get the corresponding the metal-carbene bond, okay. Very simple one, simple strategy. So here you will see that this one, you can see the first one is the strategy 1, this is the strategy 2, this is the strategy 3, okay. So different type of precursors you can take it and to make the other Fischer-carbene complexes, okay. It's quite easy, and that's why it's so popular, okay. Okay, so these are another type of metal carbene complexes where you will see that here is basically this is nothing but isocyanide complex, no, okay, but it's a functionalized isocyanide ligand, and you are using a strong base and you make this kind of a metal-carbene complexes. It's basically extension of this one, it's nothing new, okay, of the second one, okay, fine. So here you will see the strategy of the metal-carbene complexes. I'll just write down here in a very strategic way, okay. So no need to remember, so you just see the strategic way to make the metal-carbene complexes from another category of the precursors. What we are doing, I am doing here. So here you will see I am taking the metal alkyl complex where the alkyl has a alpha proton, okay. So this is the alpha proton, okay, okay, this is alpha proton, okay. Now what I am doing now, if I attack with a electrophile E plus, okay, then what will be the reaction and the product? So you will get this kind of a, so I am writing in a very general way, okay, and you will get the EH. Now if you do with nucleophile, okay, then what will happen? Ln M minus double bond Cr2 and nu, okay. So as example of electrophile is maybe the PH3 C plus, you know that, take this one. So PH3, the triphenyl carbon cation is a very good hydride or alkyl abstractor. Okay. So if you use, then what you will get, the H will be deprotonated, the alpha H will be eliminated, it will be taken by CpH3 plus and form actually this one. Okay. And you will get these carbene complexes. So you see, this is generally you will get the Fischer type carbene complexes. Okay. Now, if you in the the second case, that where you are adding the nucleophile, what will happen here? You will see, as example, like nucleophile you can take is as a base like R3P double bond CH2. So this is like a base, which will act as a nucleophile. Then you will get the this kind of carbene, and generally this strategy is followed to make the Strock carbene complexes. So it is here you will see you are adding nucleophile, that is the more electrons. That's why for this one, the precursor for the Fischer complexes, for second one, the precursor should be, that is for nucleophile attack, the metal precursor, that means this one should have less than 18 electron, that is the total valency electrons. Or if it is 18 electron, then some ligand has to come out to make the coordinately unsaturated and also to make the system less than 18 electrons, so that the nucleophile can attack on the metal center. Okay. So I am sure it is very clear now. So these are the strategies to make the Fischer and the Strock carbene from any the metal alkyl complexes. Okay, either electrophile or nucleophile. Here what we are doing here, it is as a H minus it is coming, and here it is, you will see, as a H plus it is coming. Okay, hydride or the proton, hydride abstractor or the proton abstractor. Okay, fine. So another strategy of the Fischer carbene complexes is it's a very popular and very clean reaction, that is the with the diazoalkane compound. Okay, the driving force is the formation of the nitrogen. Okay, so a varieties of precursors you can take, very simple precursor and very clean reaction, very easy reaction. You make the corresponding alkyl diazoalkane. Okay, and you will get the metal carbene bond here. Okay, so this is one of the very clean synthetic strategy. So we have discussed now total 4 synthetic strategy to make the Fischer type carbene complexes, and you can make in your own, okay, without much complexity. Fine. So it's so easy, and that's why it's so popular. Okay. So very similarly, you can also make the vinylidene complex. We already discussed in the earlier classes the classification of the Fischer, Strock, and vinylidene. And the vinylidene complexes are generally synthesized from the alkyne, okay, complexes, alkyne pi complexes. Okay, and here you will see that in presence of carbon monoxide, it forms the vinylidene fragment. Fine. So this is a route to make the vinylidene complexes from the alkyne complexes. Okay. So now I will come to the Strock carbene. Strock carbene is also regarded as a alkylidene complex, and we already discussed about what is the basic basic properties of the Strock carbene. So Strock carbene is generally formed by early transition metals and with high oxidation states. So what will be the synthetic strategy to make the metal carbene complexes? Okay, so we already discussed just 2-3 slides back about the alpha H abstraction. Okay, and this alpha H abstraction, okay, for early, it is common for early transition metals, for early transition metals, unlike the late transition metals or transition metals. Okay, and it is actually done for to reduce the steric hindrance around the metal center. Okay, so let's see. I'll give one comparative, a very interesting example. So like here, if you take the tantalum, okay, pentachlorotantalum, and you react with methyl lithium, okay, 5 equivalent, and you can nicely prepare tantalum, this one, okay, no problem, okay, you can synthesize it. But if you increase the steric crowding around the tantalum, let's say you form, okay, butyl group, tertiary butyl group, can you synthesize it? Any idea? Okay, can you synthesize this one? Any idea? Now suppose the way we have synthesized with 5 equivalent of methyl lithium, and if I can use here, this group is called new pentyl group. Okay, new pentyl group. If 5 equivalent of lithium salt of new pentyl, then can you synthesize? The answer is no. Okay, cannot. It undergoes a different and interesting and beautiful reactions. Okay, this is alpha H abstraction. Okay, alpha H elimination. Okay, so that, and what the outcome? So you will get the butyl 3CH2, okay, sorry, butyl CH2, okay, butyl CH2, 3 tantalum, okay, and here H butyl, and you will get the Me4C. So here you will see that it will undergo the spontaneous, it is not stable, you can undergo spontaneous alpha H abstraction elimination, and then you will form these metal-carbene complexes. Okay, similarly, if you start from tantalum Me3, that trimethyl, okay, and dichloro, and reacts with LiCp, 2 equivalent of LiCp, you will get this one, and then you can synthesize it. Okay, now if you use any alkyl abstractor, Cp2 alkyl abstractor, like the CpH3 plus, like this one, then what you will get? Cp2 Ta-Me, okay, that means you will get this one. Okay, so it's basically we are increasing the acidity of this methyl proton. So their steric hindrance is not much. Okay, so here it's it happened due to the steric hindrance. Now what I am doing, we here steric hindrance is medium, so medium high steric hindrance, and here a medium steric hindrance. So what we are doing, we are increasing the acidity of this CH, the methyl hydrogen, by putting cationic charge on the methyl on the tantalum center. Then what will happen? It will, in presence of strong base, as example sodium methoxide, so it will form this one Cp2 Ta tantalum CH2 and the methyl. So you will see these are the general synthetic strategy to make the shock carbene complexes. You have to put the steric hindrance around the metal center. If there is not much steric hindrance, you have to also can induce forming the carbene complex by putting cationic charge to make that proton, the alkyl proton is acidic, the alpha H proton, and then it can undergo the carbene formation reactions in presence of a strong base. So now I am sure you have realized that how you can make the shock carbene complexes. So let's say with one specific examples, we already discussed the strategy. So if you take that 1.5 equivalent of the new pentyl, this new pentyl zinc, okay, reagent, and 1 equivalent of tantalum pentachlorotantalum, then you will get 3. Okay, so this is basically butyl CH2 3 tantalum chloride, and then you with 2 equivalent of new pentyl lithium salt, and you will get the as I told that you cannot prepare this one, the butyl tertiary butyl CH2 5, you cannot prepare, it is not stable, it will undergo the spontaneous carbene formation, that is the shock carbene. Okay, we already discussed in detail in the last slide. So similarly here you will see that this tertiary butyl, as already discussed in the last slide, you can also get the tantalum this new pentyl tantalum trichlorotantalum and react with thallium Cp, and you will get then this one, and then it will undergo the carbene formation, that is alpha H elimination, and you get the corresponding metal carbene, that is the stock type of carbene complexes. And if you use a good ligand like phosphine, okay, then also you can replace the labile metal alkyl bond and you can get the corresponding metal carbene complexes. So here the alpha hydrogen elimination reaction is from the high valent is required to make it much acidic, okay, that alpha H proton, to make the reaction more feasible. So that is the strategy to make the shock carbene complexes. This is basically this complex, this is the first shock carbene complexes. Okay, fine. Okay, so similarly with different type of strategies that form a alkyne complex, if you react in presence of Bronsted acid, you can get the vinylidene complexes, and if you use the similar strategy with base, you will see here, okay, you can get the metal carbene, that is the stock carbene type complexes already discussed. Okay, so these are some of the efficient metathesis catalyst. We will discuss later about the reactivity. So this is the synthetic protocol to make the tungsten metal carbene complexes, the stock carbene complexes. These are the synthetic strategy starting from this precursor. Okay, so similar here you will see it has been used as a Grignard reagent, it has been used as a nucleophile. Okay, fine. So this discussion will not be completed without mentioning the Tebes reagent, okay, because Tebes reagent we already discussed in the beginning of the classes in a very brief way that this was this Tabes reagent is basically the stable form of the highly reactive carbene complexes, this one. So it is a kind of trapped form. So this is the trapped form, okay, or trapped, okay, or you can tell the stable form of the reactive carbene complex. This is the actually Tabes reagent, okay. So if you react with Cp2TiCl2 in presence of Me3Al, or actually this is Me2, you know that it exists as a dimer, okay, and it's actually forms this kind of metallocyclobutane type of complex with titanium aluminum, and it undergoes the carbene, that is this way, okay, and it forms the titanium Cp2 and this Tabes reagent, okay, and this acts as a Wittig reagent. You know that what is a Wittig reagent. So if you react with this one, okay, any carbonyl compound like this one, so you will get this one. So you know that Wittig reagent is, if you remember, this is the Wittig reagent. So it is a actually better reagent. In some cases the Wittig reagent is unsuccessful, but this one, the Tabes reagent, is very successful and works in some complicated scenario. So that's why it is very famous, okay, and one of the very highly used reagent to make the alkene compounds from the carbonyl compounds, okay. So these are the some strategies to make the metal carbene complexes. It's good to know, okay. You can start from here, that we already discussed in the last slide, that is this strategy, okay, and this one you can make from the this metallocyclobutane, and also from this one, okay, just by heating. So these are the different type of strategies to make the reactive metal carbene complexes, and you will see this is actually the stock type of metal carbene complexes, very stable, very reactive, sorry, the reactive metal carbene complexes, which call the Tabes reagent, okay. We in situ, as it is very reactive, so we cannot store it, but we prepare in situ. So we prepare this one, okay, and then we react, and in the reaction mixture, by slight heating, it forms this carbene and then react with carbonyl complexes, okay. So in conclusion, what we have learned the synthetic protocols for Fischer and stock carbene complexes, and you see that for the Fischer complexes, we start generally from the metal carbonyl complexes, and then we use the strong nucleophile, okay, and then we use the alkylating agent, okay, that is to make the Fischer carbene complex in general way, in general, and stock carbene complexes, you see that you make a metal alkyl complexes with high steric hindrance, so that it can undergo alpha H elimination, okay, and also with high oxidation state, so that alpha H elimination is more favorable, and then you get the corresponding metal carbon complexes. Okay. So I am sure that from today's lecture you are now will be able to set up your synthetic strategy to make the different type of carbene complexes, the Fischer and Stock carbene complexes, and you will be able to choose the reagents and the metal precursors. Okay. In the next class we will be discussing another category of metal carbene complexes that generally falls in the category of the Fischer, that is the metal N heterocyclic carbene, NHC, that is actually very useful, very famous, and you will see that later when we will come after that the Grab's catalyst. The Grab's catalyst also involves the carbene N heterocyclic carbene complexes. You can tune the properties. We have already discussed what is the NHC, NHC, that is N heterocyclic carbene. So then after that, after realizing that what is the main synthetic strategy, we will discuss the general reactivities of the metal carbene complexes, and then we will come to the mechanism and then our application in polymerization chemistry. Okay. So these are the references you can consult. Okay. These are all the very well known textbooks, and thank you very much, and see you again in the next class. Till then, bye bye.